Today's lesson is interpreting the graph of a function. So we're going to get a scenario and we're going to have to make a graph, etc., etc. But this is a real life situation and we're going to try to interpret a graph of a function. We've learned graphs of functions that are linear, that are parabolic, that are exponential, square root, and we understand how to interpret those. Parabolic, it's probably best if we talk about, I don't know, one that we wouldn't see the side, throwing a ball off of a roof of a building, but whatever. So interpreting the graph of a function. All right, so this graphic was shared by NASA prior to the Mars Curiosity rover landing on August 6, 2012. It depicts the landing sequence for the Curiosity rover's descent to the surface of the planet. If I look at this, lots of detail going on here. We will watch the video in a little bit and it'll help out, but let's just look what's going on. So we have altitude and velocity at various times. So cruise stage separation, it's the entry time. We're at -10 minutes. And then we have the entry interface. The entry time is 0. So it's almost like before entry, after entry, negative time, positive time. Various landing stages are named. Time is at 0 is called the entry interface. So up here we see the sky crane detail. This box contains detailed information about the final seconds of the landing sequence. So just the final seconds. Okay, what else do we see here? We've got negative time values, just because we want to reference the time since entry interface. So the time since entry interface would be positive time. Okay, this would be positive about 254 seconds, positive about 278 seconds, etc. So the time associated with stages before this stage would be negative. There's our negative time. And then after this stage would be positive. How about velocity? I've got a velocity as approximate numbers. We've got approximate numbers. And if you remember, velocity is distance per time. That equals velocity. And we aren't going to have any negative velocities, but the velocities shown are all positive. If we actually calculated them, because we're starting at higher altitudes and to lower altitudes, the velocities really should be negative, because we'd have, a high velocity minus a low velocity, a time that's smaller, a time that's bigger. So big minus little is positive, but you're dividing by little minus big, which would give you a negative number. Something else I can point out, if you looked really closely, those are squigglies. They look like this, and that means approximately. I use it all the time. And sometimes students ask me what it is. Sometimes they just don't know, but it means approximately. Another thing to point out or to talk about, which units, metric or US customary, make this problem easier to understand. Miles per hour is easier to comprehend when the Curiosity rover is moving really fast. And we have that up here. Oops, still in pen. Sorry, let's highlight. Super fast. So 13,200 miles per hour is easy to comprehend, but 0.75 meters per second is easier to comprehend when it's moving super slow, right? It'd be hard to do miles per hour when it's moving super duper slow. So in general, it's easier to be more accurate with metric units, which would be the meters per second. and they also just work naturally with the decimal system because the metric system is based on powers of 10. So metric units are preferred system of measurement in science, industry, engineering, but the customary U.S. units, that's what we're all used to using here in the U.S. Yeah, so when we start graphing these things, we might actually work with the metric system because we're going to work on graphing this stuff. Cool? I think that's it. Sorry, one more thing. Does this graphic, I'm reading this down here now, does this graphic really represent the landing path of the Curiosity rover? Create a model that can be used to predict the altitude and velocity of the Curiosity rover at 5, 4, 3, 2, and 1 minutes before landing. That's what we're going to work through. It's going to take us a while, but that's what we're going to work through, okay? So, mathematical modeling exercise. Create a model to help you answer the problem and estimate the altitude and velocity at various times during the landing. So, we're going to talk about units, and I told you in the last slide what units we should probably use. So we need to figure out our units and what our scale is. When we plot our graph, are we going to connect dots? Or are we going to, so connect dots like a curve or a line? Or are we going to leave dots lonely, like integers? I would connect dots. Leaving them lonely makes it like, you know, if we graphed it, that means the rover is here, and then it's here, and then it's here. That's not really how it works. The rover would be, you know, floating down on a curve. But I don't know what that curve looks like yet, so don't do that. So we're definitely going to connect some graphs. How would we describe velocity? Velocity is a hard one to describe sometimes. Altitude. So I think we've got time and we have altitude. Velocity is really a change in altitude over a change in time. How fast it's falling, right? So as the altitude gets closer to the t-axis, like the altitude, this is going to be close to the Earth, and this is going to be high in the sky. That'll be 0 time, and this will be larger time. All right, you guys are going to have to work on your paper and looking at that rover landing picture pretty closely, okay? I found another picture. It's a little bit easier to read, but you've got a picture in your classwork that's probably pretty easy to read also. So I'm going to start working up a table. So my table is going to have time, what the altitude is at a certain time, and what the velocity is. The altitude is going to be in meters because we have to label, and the velocity is in meters per second. The time is just in seconds. Time's all in seconds, so let's look through. So I looked in this really close and sort of labeled the points that were already labeled, and we can set up a table for it. So first we have time equals 0 seconds. The next time I have is 240 seconds, and then I have 268 seconds, and then 345 seconds. The altitude at 0 seconds was 125 kilometers, so I've got 125 and 3 zeros. At 240 seconds, I'm at 10 kilometers, 268, 7 kilometers, and 345 seconds, 1.8 kilometers. My velocity in meters per second, 5,900 meters per second. Whoo, doggy. 470 meters per second. 160 meters per second, and 100 meters per second. I don't need to put the units in there. I've got the units in my table. So that's the table I'm going to use to graph. Very cool, right? Whew. Okay, another sheet. So if I graph this, I'm going to have time in seconds. The most time I need is 400 and some, so I'm going to do 500. 1, 2, 3, 4. I know graphs aren't our favorite, but we can do it, right? I'm actually not going to start this at 0 because I need to see what's going on down by the ground level. So this is going to be 0. 20, 40, 60, 80, 100, 120, 140. 20,000. So this would actually be negative. 20, 30, 40,000. 50, 60, oh wait, 24, oh, see, I already forgot what I was doing. Oops. Let's fix that. So I've got 20, 40, 60, 80, 100, 120, and 140. And that is my altitude in meters. So we're doing an altitude versus time in meters and seconds. All right, I'm going to plot some points. So the first point I have, time 0, we're way up here. Okay, the next time I have, it looks like I am somewhere between there and somewhere right about there. And then we don't do much. And we don't do much again. We actually need to be around 0 though, so I've already dropped too low. Oops. So really our curve would look something like that, right? Cool. I can do the same thing with velocity. I've got time. I need the time units to be the same. So 500, 1, 2, 3, 4. And then our velocities are negative, because remember that change in time, or change in altitude over change in time, our time is actually negative. So we're going this way. 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000. Plot some points. I start out about right there with my velocity. I'm using nice big points because, well, it's just easier. 200, 250. If I had vertical lines, it would make life easier, wouldn't it? Just plotting what I have. Okay, connect some dots. And it makes sense as altitude decreases, the rover slows down. So let's try to interpret that awesome graph we just made. Does this graphic really represent the landing path of the Curiosity rover? No, because I did a stinky job, no. The height isn't really scaled very well. It doesn't really do a good job representing what we did. So I could be sweet and say the height's not scaled appropriately. According to the video that we're going to watch, it looks like the Curiosity rover rises a bit. So you'll watch the Curiosity rover goes down, and then the parachute sort of explodes and it goes up a little bit before it goes down again. So that would be why it's going to be a no, which you didn't know because you didn't watch that video yet. I'll actually link that on our Google Classroom site, so that would help. Estimate the altitude and velocity of the Curiosity rover 5, 4, 3, 2, and 1 minute before landing. Time since entry is a great way to look at that. The time since entry interface. So 2, 3, 4, 5, and 6 minutes. So if we use the graph, the landing time is about 7 minutes. Is about 7 minutes after entry interface. And you just have to convert those seconds into minutes by dividing by 60. So if I look at the graphic, I've got the altitude in miles and the velocity in miles per hour. So about 2 minutes, I'm at 45 miles, and I'm getting closer, and closer, and closer, right? My velocity is going to slow down. It's negative still because of how I'm calculating it. Slowing down and slowing down. So that's my estimated altitude and velocity. And I could graph that. I'm assuming you wrote that down, so I'm going to move to a new slide and graph it. With real paper and a real pencil, your graphs would be so much better than mine. But those are the altitude versus time and velocity versus time graphs. Based on watching the video animation, which you can watch, I'll link it. Do you think you need to revise any of your work? Explain why or why not. It depends. You know, we could, like rapid, oh, I hate when that happens. When we talk about the rapid descent, that could be a separate graph. I don't know what that is. Sorry, let's start that over. Rapid descent, it comes out very linear on our graphs. And I don't think it really is linear. So that rapid descent and that deceleration, it's not a linear movement. So the graphs don't really take into account. And then if you watch the video, when you watch the video and you see, you know, the rover comes down and then the parachute comes out and then it goes up a little bit and then back down, like we don't take that into account at all. So that's not good. Why is the graph of the altitude function decreasing and the graph of the velocity function increasing on its domain? So altitude, it's decreasing because the values are getting smaller. And then the velocity is actually increasing because the velocity is getting larger. The time values are increasing. Therefore, the velocity values are getting larger. Why is the graph of the velocity function negative? That's a tough one to figure out. Why is it negative? So it's negative because we represent velocity as a negative when the distance between two objects is decreasing, So if you look, the Mars rover is at a certain altitude, and then the Mars rover, so the distance to the ground, and the Mars rover is here, the distance to the ground. So the distance is actually decreasing. So that's why our velocity function is negative, because velocity is distance over time. So since our distance is decreasing, we make our velocity negative. That's a very scientific thing that you now know that you didn't before. The graph doesn't have a t-intercept because the Curiosity rover is traveling at negative 1.7 miles per hour when it touches the surface of the planet. So no t, oh gosh. Because it's traveling at negative 1.7 when it touches. It's not traveling at 0, it's traveling at negative 1.7 miles per hour when it touches. And we have our velocity and our time. There's no t-intercept because it goes straight past it. Let's see, I think we're going up and over. It just doesn't cross the t-intercept. What is the meaning of the t-intercept? T-intercept would be the time when the rover lands on the surface of Mars. And then we've got the y-intercept is the height of the rover when entry interface begins, because that's when we start our time. Wow, this slide looks awful now. I'm so sorry. Whew. All right, let's try something different. I've got a Mars rover collected the following temperature data over 1.6 Martian days. A Martian day is called a sol. Use the graph to answer the following questions.
All right, this is super duper important. And I'm going to try to go through it somewhat slow, even though this lesson is getting pretty long. So, approximately when does each graph change from increasing to decreasing? Let's do that first. So, if you look at this graph, we're decreasing. We increase a little bit, decrease a little bit, increase, decrease, increase. So for air temp, we're looking for the points of inflection. That one's a little tough. That's questionable. Okay, that one's a little easier. So I'm just going to write down what's going on. So I have increasing to decreasing for the air. It's at approximately 10.18 and around 10.59. And then I've got the increasing to decreasing for the ground. And I put the marks on the graph, the black highlighty marks and the sort of red ones. That's about 10.52, I'm guesstimating, which you're going to do too. And these are all in sols. But now we need to find the points of reflection for decreasing to increasing for the air and the ground. I'm going to push pause and highlight the points. So here I've gone through and I've looked for where my graph changes from decreasing to increasing, so that point of change where it sort of turns. I put some little hash marks there, so it looks like approximately 10.12, 10.25, and 11.2 for the air. And then the ground, we've got about 10.2, 11.1, and 11.2 Sol. Now, what we do now is just look at the air temperature. I need to write things in interval notation. So I gathered all my data up here, and now I need to write it in a way that's easier to look at, easier to analyze. Now, the air temperature increasing on the interval, we're going to go with 10.1, oh gosh, did not mean to do that, pushed the wrong button. 10.12 to 10.18 is when it's increasing. So I'm going to bracket it 10.12, 10.18, and then again 10.25 to 10.59. So those two intervals. And then one more interval. I have 11.2 to the end, where we stop reading it at. So I have 11.2 to 11.5, because we don't know what happens after 11.5. All right, I'm going to need this information for number 9, but you should have it written down, so I'm going to move to the next slide. Temperature decreasing for ground. I've got intervals again, about 10 to 10.2, and then again from 10.55 to 11.1, and then again from 11.414 to 11.2. That's my interval notation for both of those. And then what is the air temperature change on this time interval? Let's see. If you look at the graph, let me bring it in here. Air temperature change. If you look at the graph, it looks like the high for the air temperature is about about 28 degrees Fahrenheit is my high, and my low is negative 103 degrees Fahrenheit. That means my change, my delta is 131 degrees Fahrenheit. Cool. It's funny, this is listed in Fahrenheit, and that is listed in Celsius. You could have gone Celsius for this one and just read it from the vertical axis. Why do you think the ground temperature changed more than the air temperature? Is that typical on Earth? Not typical on Earth. The ground temperature takes longer to change. But really, that's a matter of opinion. I don't think it's typical on Earth. Maybe because the change is so drastic that the ground changes more. That's my non-scientific analysis. And then, is there a time when the air and the ground temperature were the same temperature? Explain how you know. When they intersect. We've learned that things are the same when they intersect. Oh gosh. So if you look at the graph at about 10.3 Sol, and then at about 10.62 Sol, and then at about 11.3 Sol, the temps are the same. Whenever two lines cross on a graph, the information is equal, right? Okay, that was really long and sort of difficult, and I would deem the end of the lesson as the most important, so I hope you sort of picked up on that. Cool, cool.